In this section, we'll talk about some basic theory of linear differential equations. A linear differential equation of order n is an equation that can be written in the form a sub n times the nth derivative of y plus a sub n minus 1 times the n minus first derivative of y plus dot 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 all the way down to a naught times y equals b, where a naught through a n and b are functions that depend only on x, not on y. And when a naught through a n are all constants, we say that equation 1 has constant coefficients. Otherwise, it has variable coefficients. If b of x is identically equal to 0, equation 1 is called homogeneous. Otherwise, it is non-homogeneous. In developing a basic theory, we assume that a naught through a n and b are all continuous functions on an interval I, and that a sub n is not equal to 0 on that interval I. Then, on dividing by a sub n, we can write the equation 1 in the standard form: the nth derivative of y plus p1 times the n minus first derivative of y plus dot 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 plus p sub n of x times y equals g, where the functions p1 through pn and g are continuous on I. For a linear higher order differential equation, the initial value problem always has a unique solution. And I'll point out that we have the following relationship here, that p1 of x is a n minus 1 of x divided by a sub n of x, and that g of x is b of x over a n of x. So all of these constants here have been divided by a sub n of x. We then have the following existence and uniqueness theorem. So suppose that p1 through pn and g are each continuous on an interval ab that contains the point x naught. Then for any choice of the initial values, gamma naught, gamma 1 up to gamma n minus 1, there exists a unique solution y on the whole interval a comma b to the initial value problem, the nth derivative of y plus p1 times the n minus first derivative of y plus dot 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 plus pn times y equals g, with initial conditions y at x naught is gamma naught, y prime at x naught is gamma 1, up to the n minus first derivative of y at x naught equals gamma n minus 1. So let's see how this existence and uniqueness theorem applies to a specific initial value problem. So for the initial value problem given by x times x minus 1 times y triple prime minus 3x y double prime plus 6x squared times y prime minus cosine of x times y equals square root of x plus 5, with initial conditions y at x naught equals 1, y prime at x naught equals 0, and y double prime at x naught equals 7, determine the values of x naught and the intervals a comma b containing x naught, for which theorem 1 guarantees the existence of a unique solution on the open interval from a to b. So our first step is we want to write this initial value problem in the standard form, which means that we have to divide by the leading coefficient here. So when we're starting to write how the standard form, it looks like this. we have y triple prime with the leading coefficient of 1, and then minus 3x over x times x minus 1, and that is multiplied by y double prime, and then we have 6x squared over x times x minus 1 times y prime, and then minus cosine of x over x times x minus 1, and that function times y, and then that equals square root of x plus 5 over x times x minus 1. Now, what I'm going to do here is I'm going to look at these three functions first, because what I see there is all these functions have a numerator that is a continuous function on the entire real line. So 3x is continuous everywhere, 6x squared is continuous everywhere, and cosine of x. Here on the right-hand side, we have a square root of x plus 5 in the numerator, and the domain of that function is not the whole real line. So we're going to do that one separately. So let's take a look at these three functions, right? So we have negative 3x over x times x minus 1, and then 6x squared over x times x minus 1, and then cosine of x over x times x minus 1. We can put a minus in front of that. If we look at these functions, the only problem points that occur here are when we divide by 0. And so the domain of these functions are all real numbers except for 0 and 1. So these functions are continuous everywhere except, so everywhere except when x equals 0 or when x equals 1. So again, those are the values that make the denominator equal to 0, and we cannot have division by 0. Now, to write that in fancy interval notation, we have to exclude those values. And so if we look on a number line, the values that we have to exclude are 0 and 1. So that's where the functions are not continuous. So in interval notation, we have an interval from negative infinity to 0, then an interval from 0 to 1, and then from 1 to infinity. So this is continuous on and let's write that down as follows. So in interval notation, this is continuous on negative infinity to 0, union 0 to 1, union 1 to infinity. Okay, so now let's take a look at square root of x plus 5 over x times x minus 1. Now, the first thing we need to note is that square root of x plus 5 is continuous everywhere it's defined, and that is when x plus 5 is greater than 0. In other words, when x is greater than or equal to negative 5. And we can write that in interval notation as negative 5 to infinity. Now this function has the same problem with its denominator, so it's not defined on it's not defined at 0 and 1. So now let's take a look at that interval from negative 5 to infinity. So we can write negative 5 here, and then that interval from negative 5 to infinity looks like that. And if we combine those two, so it needs to be greater than or equal to negative 5, and it cannot be 0 or 1. What we see is when we cross out those two values at 0 and 1, that we get the interval, so the entire function, is continuous on negative 5 to 0, right? That's this interval. And then union 0, 1, union 1 to infinity. Now, to know where all of these functions are continuous, we have to look at the intersection of these two sets. So what do these two have in common? Well, we can clearly see 1 to infinity is in both, 0 to 1 is in both, and then we need to look at the smaller of these two. So that is negative 5 to 0. So the entire differential equation in standard form, these four functions are continuous on so let's take a look at the actual theorem. We had to look at P1 and then P2, P3. So this is our P1, this is P2, and this is P3, and then this is g of x. So, and that's a condition for this theorem, right? P1 through Pn and g of x need to be continuous on an interval. So our conclusion here is that P1 of x, and let's use a different color here. Let's erase this here. So we have that P1 of x, P2 of x, and then P3 of x. Those are these three functions. And then g of x, that's our function here, we've now shown that these are continuous on the union of these intervals. And let's make them all open intervals. So we have -5 to 0, union 0 to 1, and then union 1 to infinity. So now, depending on where x naught is, we have to pick one of these three intervals. So if our initial value x naught is in -5, 0, then we have a unique solution on that interval. Now, if x naught is in the interval from 0 to 1, then there is a unique solution on 0 to 1. And then finally, if x naught from the initial condition is in the interval 1 to infinity, then there is a unique solution on the interval 1 to infinity.